introduction, let's look at a couple of key linkage techniques here. There are three techniques that we're going to discuss in a little bit more detail. Deterministic linkage, probabilistic linkage, and some, as we label them here, computer science methods to linkage. They are techniques that, at least in some part, are familiar to you guys, and there's no need here to go into all the technical details, but at least you should be aware of them. So let's start with deterministic rule-based linkage. It's a very simple method for matching different data sets. You assert your data, so you aim for an exact match using usually one key unique identifier to do so. If you have multiples, the identifier have equal weights, and they're chosen usually by the researcher themselves. So the table that you see here is one example where matching is done with the Social Security numbers. And you see here that in dataset A and dataset B, we have two SSNs that match. And the remaining case or record in set B can't be matched because the Social Security number is missing. A common problem, and you can already see that this method only works well if you have a perfect key and if the key is present in all data sets that you want to merge. As soon as that is not the case, you have to start moving on to next best variables, in this case name. But as a quick glance at the table will show you is that here too names can be spelled differently and have issues that would make this kind of deterministic rule-based linkage much more difficult. For this reason, a couple of other techniques have been developed. The basic idea is quite old, from Newcomb and Kennedy in the 60s, and the theoretical piece to that was developed by Felicki and Sunter. Here, in this approach, a wide range of potential identifiers or keys can be used for record linkage. Computing the weights is based on estimated ability to match or not match them. So there's a frequency ratio that gets computed. I'll show you in a second how that works. And unlike the rule-based method that we just talked about, here we can use algorithms that can be trained. One problem is that estimating these errors and thresholds, we'll go into that in more detail in a moment too, require an independent assumption and clerical review. Both of them manually labor-intensive or questionable. So what's often done is there will be two probabilities estimated. The probability that a field agrees, given that the pair of records is a true match, and the U probability, the probability that a field agrees, given that the pair of records is not a true match. Let me just give you a quick example of what that would be for a U probability. If you have month of birth in one record and in another, then you have a 1 in a 12 chance that the field agrees, given that the pair of records is not a true match, and just by the probability distribution in here. So these kind of probabilities are important in the thinking of Felicki and Sunter. Let's assume we have two data sets, A and B, and the goal is to find the true matches, the union of the two, where the entities are indeed the same, and separate them out from the U records, which are entities that are in both data sets, but not true matches. A vector of variables can be used as a comparison, and the comparisons are done in pairs. So every X and every Y variable case record from each of these two data sets would form a pair, and all pairwise comparison would be made in theory. Then there's a decision rule where we look at the probability of the sector of covariates given that there's a true match over the probability of the sector of covariates given that this particular pair is not a true match. If that ratio is larger than a set threshold, it's considered a match. If it's smaller than that set threshold, it's considered a non-match. As I said, the assumption behind this is conditional independence. So given a pair of records representing the same entity being a true match, we assume that the agreement in each field is independent of the agreement in other fields. This is really mostly a mathematical convenience. In reality, that is usually not the case. You can have area codes that covary with geography, first names that covary with sex, and a lot of other examples like that can be found. Age and marital status, you can come up yourself with a few quite easily. So how does this then work? Assuming we make this convenience assumption, we have first each matching variable compared and assigned a score, the weight based on how well it matches. Then there is a frequency analysis of the data values. Uncommon values tend to agree or tend to show stronger evidence for linkage. Remember when we had common values like the name Julia Lane versus, let's say, my name. There's different linkage evidence for these two. Then you calculate a score for each field that indicates for any pair of records how likely it is that they both belong to the same entities. You sum the scores over all the fields. You sort your record pairs in the order of their scores and then find the right matches. Now that can be very intensive, right? All pairwise comparison is quite inefficient, and therefore something called blocking will be quite critical, and we get to that in a second. So what are the issues? First one, which models do we use to estimate the M and the U probabilities? That's a typical modeling issue. How do we set the thresholds? A question of evaluation of the model. Then the question, which variables do we use, or which features do we use to do that comparison? Known to the computer scientists as a problem of feature engineering. And finally, I mentioned it already a couple of times, how do we avoid looking at all possible pairs? The sufficiency problem. If my set A has 100 cases and my set B has 1,000 cases, then I'm looking at 100,000 possible comparisons. And that, of course, can be quite intensive, given that we're often dealing with millions of records. So remember strata from earlier modules that we had. The same idea can be applied here. It's usually called blocking, and the idea is that in a simple blocking that you compare all pairs that hash to the same value, so they belong to the same city or same birth year, and then within those you search for the matches. Of course, you could think of extensions where you block on multiple attributes and take the union of all pairs found, or you pick ordered attributes and sort. So similar to the strategies that we have seen in sampling, here too you can be a little bit more efficient in terms of computational power. Now all of this should ring a bell. The task at hand, finding a similar case, finding a good match, might remind you of other techniques you've seen. Clustering techniques, modeling techniques that solve prediction problems. Actually, even when creating the weights, we've looked at propensity score matching. We tried to find for non-responding cases in the respondent set that are quite similar. So no surprising here that we have in this record linkage context, clustering algorithms or prediction algorithms that are quite similar to methods that you've seen before. So the advanced techniques, they shouldn't scare you. In fact, you probably would be able to adapt the methods you've seen before to fit this particular problem. So just here one example for a comparison, or visual comparison here for probabilistic versus machine learning approaches in linking. And we have our source file and target file. We can use the blocking strategy, do a similarity computation, and have a matching decision in the Felix-Santa approach. In the machine learning approach, take a similar first step, but then if we have a training data set, hence a set of data where you already know what are the true matches, that can help you find the right or even better covariates that finally go into the model itself. So it solves one of the problems that we mentioned before, namely the modeling issue, which features should be used, which weight should they have, and the like, making the whole thing more efficient in addition to the blocking that we discussed before. So in this very brief overview over key record linkage techniques, let me summarize that. We have deterministic matching, which is a rule-based method. We have probabilistic record linkage, mostly known by the Fellagy and Sunter paper. It's a way to use available attributes for linking, many of them, and calculates match weights for attributes in the file. And then finally, we have computer science approaches, many of them based on machine learning, data mining, database techniques. And we'll have in the next module additional material for you to review those, even so there's not a video introducing them. Finally, some software that is free and available for you to play around with on the web, Link Plus, the linking, ChoiceMaker tool, FEBRL, and the Merge Toolbox. They all have quite good user interface. All of them have some restrictions, but depending on your needs, we strongly recommend that you try them out. Thank you.